Our universe might be just one of countless others. This is the multiverse, a concept that physicist Brian Greene describes not as a convenient fiction, but as a natural consequence of our best scientific theories. In the next few minutes, you will gain a complete mental map of how these infinite realities could be structured and interact. What if the Big Bang was not a unique beginning, but one event in a much larger cosmic process? We will journey through the scientific architecture of parallel worlds, from quantum branching to colliding dimensions, and discover the mechanisms that might allow them to communicate. This exploration redefines everything we know about reality and our place within it. What single question about existence would you most want answered by exploring other worlds? This cosmic tapestry finds its first scientific thread in the theory of eternal inflation. Picture the Big Bang not as a singular, explosive beginning for everything, but as one local event within an eternally expanding background. Imagine a vast, bubbling cosmic ocean, where the space between galaxies is not truly empty but filled with a strange, high-energy state. In this ocean, random fluctuations can cause a tiny patch of space to suddenly drop its energy, like a bubble spontaneously forming in boiling water. That drop triggers a local Big Bang, and that patch inflates at an incredible speed to become an entire universe, complete with its own galaxies and stars. Crucially, the surrounding ocean of high-energy space continues to expand, and new bubbles are constantly forming within it. Each of these bubbles is a separate universe, forever drifting apart within an unending, inflating metaspace. This process is not a one-time event but a continuous, eternal creation machine, generating a limitless multiverse where each universe can have different properties frozen into place during its birth. Our entire observable cosmos, with all its hundreds of billions of galaxies, could be just one such bubble in an infinite froth of reality. But the sheer scale of this first level of the multiverse is almost impossible to grasp. Think of our entire observable cosmos with its hundreds of billions of galaxies, each containing billions of stars. Now picture that entire vast expanse as just a single grain of sand on an endless beach. This is the Level 1 multiverse. The space beyond our cosmic horizon is not empty. It is filled with more of the same, an infinite expanse of space, time, and matter. Because the universe is expanding at an accelerating rate, the light from these distant regions can simply never cross the void to reach us. They are forever beyond our view, islands separated by an ever-widening sea of nothingness. Yet if the whole cosmos is truly infinite and the laws of physics are the same everywhere, then the arrangement of particles in those distant volumes must eventually repeat. With an infinite number of cosmic grains of sand, every possible arrangement of matter must occur not just once, but an infinite number of times. Somewhere out there, a perfect duplicate of you is reading these very words, living a life identical to yours in every detail. Another version made a different choice this morning and is living a completely separate life. This isn't science fiction, but a direct mathematical consequence of infinity. As the physicist Alan Guth suggests, in an eternally inflating universe, anything that can happen will happen, and it will happen an infinite number of times. This model presents a cosmos of unimaginable vastness, where realities are separated not by magic, but by simple, insurmountable distance. It sets a profound foundation, but the architecture of the multiverse only grows stranger from here. That cosmic vineyard of identical universes is just the beginning. Now picture that same vineyard, but this time each grape is a different variety, with its own unique flavor, color, and texture. This is the Level 2 multiverse, a realm where the bubbles are not just separated by distance, but by the very laws of physics themselves. In this breathtaking landscape, gravity might be a crushing force in one universe, while in another it is a gentle whisper. Some of these realities might be so unstable they collapse in an instant, while others are so empty and cold that not a single atom could ever form. This staggering diversity emerges from the heart of string theory and its concept of a cosmic landscape. The idea is that the vacuum of space is not a single, simple state, but can exist in many different stable configurations, like a vast cosmic terrain with countless valleys. When a new bubble universe forms, it randomly settles into one of these valleys, locking in a specific set of physical constants and forces. The strength of electromagnetism, the mass of an electron, the very number of dimensions of space, all become frozen accidents of a universe's birth. In a cosmos where the cosmological constant is just slightly larger than our own, the universe would have expanded so rapidly that not a single star would ever have had a chance to shine. Life as we understand it becomes an impossible dream in an overwhelming majority of these realities. Our own universe, with its seemingly perfect balance for complexity, is not a special creation, but simply one lucky ticket in an infinite cosmic lottery. This introduces a profound question. If the rules of reality are not universal but local, what does that say about our own place in the grand scheme? The architecture of the multiverse suggests that the constants we hold as fundamental are not necessary truths, but merely the conditions of our particular neighborhood. This shifts our perspective from a universe fine-tuned for life to a multiverse so vast that a habitable neighborhood was bound to appear somewhere. The sheer variety is almost beyond comprehension, a tapestry woven from threads of different physics, each creating a reality alien to the next. This branching of reality begins at the most fundamental level. When a single electron is measured, its position is not a mystery that resolves into one location, but a moment of division where the universe splits, creating one branch where the electron is here and another, equally real branch where it is there. This process scales up dramatically from the quantum to the human scale. Your decision to turn left on your walk does not cause the split. Rather, it is the culmination of trillions of quantum events in your brain that lead to that single conscious thought. At that precise moment, the universe fractures, creating one timeline where you turn left and see a blue car, and another where you turn right and notice a flowering tree. There are no what-ifs, only what is, across an ever-expanding tapestry of actualized possibilities. In this view, every version of history that could have happened did happen. A world where the Library of Alexandria never burned exists in its own branch, as does a reality where you took that different job offer last year. This is the profound, and for some, unsettling, implication of Hugh Everett's many worlds interpretation. There is no single collapsing probability wave, only an endlessly dividing river of actuality. As physicist David Deutsch notes, the multiverse is not an extra idea we add to physics, but a direct outcome of the equations we already trust. These countless parallel worlds are not far away in space, but layered atop one another in an abstract quantum realm known as Hilbert space. They are separated not by miles, but by their decoherence, a process where the different branches lose the ability to interfere with one another, becoming independent stories in an infinite cosmic library. This raises a deeply personal question about the nature of our own path. If every choice we make is mirrored by another version of ourselves who made the opposite choice, what does that say about free will or the significance of the life we are living? This architecture suggests that our journey is not the only one, but it is no less real for it. The narrative of our existence is simply one thread in a fabric of unimaginable complexity, a single melody in a symphony of infinite variation. Even the infinite branching of quantum worlds and the cosmic bubble bath of universes operate within a consistent mathematical framework. We now step beyond physics entirely into the realm of pure abstraction. The mathematician and physicist Max Tegmark proposes a final, staggering level of the multiverse, one where existence is not defined by space, time, or quantum fields, but by mathematics itself. In this level 4 multiverse, every mathematically consistent structure is not just a description of a reality, it is a physical reality. If a set of equations can describe a coherent universe, then that universe exists. Our own cosmos, with its galaxies and planets, is simply one specific mathematical structure that has the peculiar property of containing self-aware observers within it. As Tegmark himself states, our external physical reality is a mathematical structure. This means that universes with 7 spatial dimensions, or realities built on geometric forms we cannot even visualize, have just as much claim to existence as our own. The architecture here is not one of cosmic inflation or quantum splitting, but of an infinite, timeless landscape of abstract mathematical possibilities. This perspective forces a radical redefinition of what we mean by existence. It suggests the multiverse is not merely vast, but truly complete, containing every conceivable form of being, from a universe that perfectly mirrors a game of chess to one that operates like a vast cosmic symphony. But if every mathematical structure is its own separate reality, what possible bridges could ever connect them? This abstract framework brings us to the ultimate frontier of cosmic architecture, the mechanisms that might allow these infinite realities to interact. Our own universe might be a 3-dimensional island adrift in a higher dimensional sea. This is the startling picture painted by brane cosmology, where the word brane, short for membrane, describes our entire reality as a single slice within a cosmic loaf. Each slice is a parallel universe, and the space between them is not empty, but a vast, higher dimensional realm physicists call the bulk. Think of a collection of photographs scattered on a table. Each photo is a complete, 2-dimensional world to the people living inside it, utterly unaware of the other pictures lying just millimeters away. In the same way, other 3-dimensional brains could be floating incredibly close to ours in these unseen dimensions. The reason we cannot see or touch them is that every particle and force we know of, from light to matter, is glued to the surface of our own brain. They are like actors on a stage, unable to step into the audience. But there is one profound exception: gravity. Gravity, in this model, is not a force confined to the brain, but a fundamental curvature of the entire higher dimensional bulk. This means it can leak or seep between adjacent universes. A gravitational wave from a colossal event in a neighboring brain could, in theory, ripple through the bulk and gently tug at our own space-time. This provides a potential bridge, a whisper of interaction between realities that are otherwise completely separate. The implications are staggering. Our Big Bang might not have been a singular beginning from nothing, but the aftermath of a cataclysmic collision between our brain and another. Such an event would have released an unimaginable firestorm of energy, seeding our entire cosmic history. This architecture transforms the multiverse from a collection of abstract possibilities into a dynamic, geometric structure where universes could literally bounce off one another, leaving echoes of their contact in the deepest patterns of our cosmos. What faint gravitational tremors from a neighboring reality might we one day detect in the void? A universe might not need to be a place at all, but a kind of cosmic data structure. The holographic principle proposes that our seemingly solid three-dimensional cosmos, with its swirling galaxies and deepest voids, is actually a projection, like a magnificent hologram emerging from a flat, two-dimensional surface at the very edge of everything we can know. This is not a metaphor from science fiction, but a serious idea born from the study of black holes. When physicists calculated how much information a region of space could contain, they made a startling discovery. The maximum information is not proportional to the volume of the space, as you might expect, but to the area of its boundary. Imagine a sphere. Instead of the information about everything inside it being stored throughout its three-dimensional volume, it is entirely encoded on its two-dimensional surface, like the information for an entire three-dimensional movie being stored on a flat, two-dimensional Blu-ray disc. Our reality, in this view, is the movie being played back, as physicist Leonard Susskind, who helped discover the principle, explains. The three-dimensional world of ordinary experience might be a hologram emerging from a two-dimensional reality. This completely inverts our intuition about how reality is built. What we perceive as depth, substance, and distance are all emergent properties, a grand illusion generated from a vast, complex calculation happening at the periphery. This radical notion forces us to reconsider the very fabric of existence. If our universe is a projection, what is the projector and where is it located? The architecture of the multiverse transforms under this principle. Separate bubble universes might not be the fundamental reality. Instead, they could all be different projections, different movies being played from a single, shared two-dimensional screen. This common underlying informational substrate could be the deepest layer of reality, a cosmic hard drive from which all possible universes are rendered. The separation between realities would then be an illusion, a consequence of different data streams running on the same fundamental hardware. This perspective offers a potential mechanism for interaction that bypasses the need for travel through space. If two universes are projections from interconnected parts of this substrate, a fluctuation or a link in the code could allow information to leak from one reality to another. Such a connection would not be a physical bridge, but an informational one, challenging our core ideas about locality and what it means for two things to be separate. The echoes we might detect could be glitches in the matrix, subtle correlations in the cosmic background radiation, or strange quantum entanglements that have no local cause. We are left to wonder if the deepest laws of physics are not about forces and fields, but about information and computation, guiding us toward the ultimate source code of the multiverse. A ghostly current is pulling at the very fabric of our cosmos. Across unimaginable distances, entire clusters of galaxies are drifting together in a coherent stream, like leaves caught in a slow cosmic river. This phenomenon, known as dark flow, presents a profound mystery. The motion is too vast and too uniform to be explained by the known distribution of matter in our universe. It is as if a tremendous gravitational tide is washing through space, its source lying beyond the edge of everything we can see. Cosmologist Alexander Kashlinsky and his team detected this strange signal by meticulously studying the cosmic microwave background, the ancient afterglow of the Big Bang. They found that these galaxy clusters are all moving in the same direction at incredible speeds, suggesting they are being pulled by something truly colossal. The leading hypothesis is both simple and staggering. This pull could be the gravitational influence of another universe, a neighboring reality in the vast multiverse. Recall the brane cosmology model, where gravity is the only force that can seep between dimensions. Dark flow could be the first faint whisper of that seepage, a gentle tug from a cosmos lying parallel to our own. This is not a science fiction fantasy. but a potential observational clue that the walls between realities are not absolute. The architecture of the multiverse might allow for these subtle, long-range gravitational conversations across the void. While the findings remain controversial and require further confirmation, they offer a breathtaking possibility. We may not need to build a starship to find evidence of other worlds. We might simply need to chart the strange, silent currents flowing through the darkness of our own space, listening for the gravitational echoes of our cosmic neighbors. The faintest tremor in the cosmos could be the echo of a universe being born. Deep within the fabric of space-time, gravitational waves ripple outward from the most violent events imaginable, like the collision of two black holes. But what if some of these ripples originate from a far more profound source? The moment our own reality was forged in a clash of worlds. In brane cosmology, our Big Bang was not a singular beginning from nothing, but the explosive aftermath of our three-dimensional brain colliding with another in the higher dimensional bulk. The energy released would have been beyond comprehension, a firestorm that set our entire cosmic history into motion. The lingering vibrations from that primeval event would still be washing through the universe today, a faint hum encoded in the gravitational wave background. This is not just a theoretical idea, it is a testable prediction. Observatories like LIGO and the future space-based detector LISA are designed to listen to the universe's vibrations, and they are sensitive enough to potentially hear this ancient whisper. Finding a specific, all-pervading signal in that data would be like finding a fossil from the moment of creation itself, a smoking gun for a dynamic, interacting multiverse. Even critics of the theory, like physicist Paul Steinhardt, emphasize the vital importance of chasing such evidence, of testing our boldest ideas against the cold, hard data of observation. This search transforms the question of our origins from a philosophical puzzle into an experimental one. It suggests that the architecture of the multiverse is not static, but a scene of dramatic encounters where universes are born from violent embraces. If such a foundational interaction is possible, what about more subtle, ongoing forms of influence that might be quietly shaping our reality even now? Two particles born from the same quantum event can remain linked in a perfect dance no matter how far apart they fly. This is quantum entanglement, a connection so strange that Albert Einstein himself called it spooky action at a distance. If you measure one particle and find it spinning upward, its partner, even if it is now on the other side of the galaxy, will instantly be found spinning downward. This correlation happens faster than light, challenging our most basic ideas about space and locality. It seems as if the universe is not playing by the rules of separate, isolated objects, but is instead a single, deeply interconnected whole. This spookiness might be more than just an oddity within our universe. It could be a profound clue that the architecture of reality includes connections that transcend a single reality. A fascinating idea known as the ER equals EPR conjecture, explored by physicists like Juan Maldacena, proposes a radical solution to this mystery. It suggests that every pair of entangled particles is not communicating faster than light through empty space, but is instead connected by a microscopic wormhole, a tiny bridge in the fabric of spacetime itself. In this view, entanglement is not spooky action, but a geometric connection, a shortcut through the hidden folds of the cosmos. Now expand this idea into the multiverse. If entanglement can forge tunnels through our own spacetime, could it also create threads that stitch across the boundaries between different realities? In the many worlds interpretation, when the universe splits, the branches might not be completely severed. Subtle quantum entanglements could persist, linking your life here with the lives of your other selves in parallel timelines. In the brane cosmology model, perhaps the gravitational leakage between worlds is facilitated by a vast, underlying web of entanglement connecting one membrane to another. While this remains highly speculative, it paints a picture of a multiverse that is not a collection of isolated bubbles, but a single, coherent structure woven together by countless quantum threads. The separation between realities may be an illusion, a consequence of our limited perception, while at the most fundamental level, everything remains connected. This suggests that interactions between worlds are not always colossal events like brane collisions. They could be subtle, constant, and woven into the very quantum code of existence. The ghostly pull of dark flow and the faint hum of primordial gravitational waves might be the loud, obvious signals, but the true conversation between realities could be a silent, instantaneous whisper happening everywhere at once in every entangled particle. What does it mean for our own reality if the choices we make and the paths we take are subtly influenced by, or even influencing, the infinite versions of ourselves living in worlds just a quantum thread away? Our universe's perfect balance for life appears less like a miracle and more like a cosmic address. Why do the fundamental constants seem so precisely set for our existence? The answer might lie not in a grand design, but in a simple, powerful idea known as the anthropic principle. In a multiverse of infinite variety, most realities are sterile voids or fleeting flashes of energy, utterly incompatible with any form of life. We could never find ourselves in such places, asking why the universe is the way it is. Our very presence as observers acts as a filter, guaranteeing that the universe we measure is one of the rare, habitable ones. This is not evidence of fine-tuning by a creator, but a profound form of selection bias on a cosmic scale. As physicist Brandon Carter proposed, what we can expect to observe is restricted by the conditions necessary for our presence. Our universe's seemingly perfect gravitational constant and cosmological constant are not special in the grand scheme of things. They are simply the local bylaws of our particular cosmic neighborhood. This principle reframes the greatest question of existence. Instead of asking why the universe is fit for life, we realize that life can only arise in a universe that is fit for it. The vast, indifferent architecture of the multiverse makes our reality not a planned destination, but a statistical inevitability in an ocean of silent, empty worlds. This selective interaction, where consciousness itself determines the slice of reality we perceive, forces a deeper question about the observer's role. Are we merely passive residents of a lucky universe, or does our active observation play a more active part in defining the reality we call home? The very act of looking might be what solidifies the path you walk. In the traditional Copenhagen view of quantum mechanics, a particle exists in a blur of all possible states until a conscious observer measures it, forcing the universe to choose one definite outcome from the haze of probability. This places the human mind in a strangely powerful position, as if reality itself waits for our gaze to snap into focus. Yet in the many worlds interpretation, this moment of choice is an illusion. There is no collapse, only a branching, and the observer is swept along into one timeline among countless others, a passenger on a river that endlessly divides. Both views grapple with the same mystery. The transition from the quantum may be to the concrete now, but what if the truth is even more intimate? The physicist John Archibald Wheeler proposed a radical idea he called the participatory anthropic principle. He suggested that the universe only comes into a tangible state of being through the act of observation. In this view, consciousness is not a latecomer to a pre-existing cosmos, but a fundamental player in its very creation. It is as if the universe is a vast, unformed question, and our observations are the answers that give it shape. Within a multiverse of infinite branches, this concept transforms from a philosophical curiosity into a potential mechanism. Your stream of conscious experience might not be randomly assigned, but actively selecting its way through the garden of forking paths. Every decision, every moment of awareness could be tuning your perception to one specific reality track, while other versions of you with subtly different focuses resonate with different branches. This does not mean you can simply wish yourself into a universe with different physical laws, but that your conscious perspective might be the very filter that determines which slice of the infinite multiverse feels real to you. The separation between worlds then becomes not just a matter of quantum decoherence or cosmic distance, but a separation of attention. The architecture of reality gains a deeply subjective layer where mind and cosmos are woven together into a single, inseparable whole. This leads us to the final, haunting edge of this exploration. If consciousness is the selector, what are the limits of what it can select? Could there be realities so alien, governed by logic and mathematics we cannot comprehend, that no form of awareness from our world could ever latch onto them? The ultimate border between universes may not be in space, but in the very capacity to know. This digital frontier reframes the very substance of existence. Our universe, with its galaxies and gravity, might not be a fundamental reality, but an incredibly sophisticated simulation running on a computer in a higher-level existence. This is the simulation hypothesis, a modern echo of Plato's allegory where prisoners mistake shadows on a cave wall for the whole of reality. If this is true, then the entire multiverse could be something far more structured than a cosmic bubble bath. It might simply be a vast server farm, where each separate universe is a different simulation instance running on the same inconceivable hardware, or perhaps a completely different software program. The philosopher Nick Bostrom formalized a startling statistical argument for this. He suggests that if any advanced civilization ever reaches the technological capability to run detailed simulations of its own history, it would likely run a vast number of them. In that scenario, the number of simulated minds would overwhelmingly outnumber the minds in the original base reality. Therefore, if such simulations are possible, it is statistically probable that we are among the simulated. This architecture transforms the laws of physics from fundamental truths into the programmed rules of the simulation, the underlying code that governs our reality. In this model, what we perceive as the unbreakable speed of light or the force of gravity could be nothing more than processor limits or carefully designed parameters to keep the simulation stable and efficient. The barriers that separate our universe from others in the multiverse are not vast expanses of space or different quantum branches, but firewalls of code and access permissions. Interaction between these simulated realities would not require traveling through a higher dimensional bulk, but could be as simple as a data packet transfer between servers, or as catastrophic as a system-wide update that alters our core constants, or even a complete system crash that ends our local universe. This computational hierarchy presents a chillingly elegant answer to the multiverse's architecture. It suggests that all the levels we have explored, from eternal inflation to quantum branching, could themselves be emergent phenomena within a grand digital construct. The faint glitches we might detect in the cosmos, like strange quantum correlations or unexplained particles, could be the equivalent of cosmic background radiation for this digital universe, hints of the underlying computational substrate. This perspective forces a profound comparison. Is the true nature of reality an endless cosmic landscape of mathematical structures, or is it an unimaginably powerful computer, patiently rendering every detail of our existence? The answer depends on where we look for the final layer of causation, in the timeless language of mathematics or in the logical execution of a program. Each blueprint for reality comes with its own unique strengths and profound limitations. The Level 1 multiverse, a cosmic expanse of infinite space, is perhaps the most conservative model. It requires no new physics, flowing naturally from the well-established principles of eternal inflation and a boundless cosmos. Its greatest weakness, however, is its ultimate untestability. Those duplicate versions of you exist, but they are imprisoned forever beyond our cosmic horizon by the accelerating expansion of space itself. We can deduce their existence, but we can never visit or observe them. The Level 2 landscape multiverse, with its bubbles of different physical laws, is deeply motivated by string theory. This gives it a strong mathematical appeal, suggesting why our universe's constants are what they are. Yet this strength is also its core weakness, for string theory itself remains a beautiful, unverified framework, lacking any direct experimental confirmation. The quantum multiverse offers an elegant solution to the strange measurement problem in quantum mechanics, removing the need for a mysterious collapse of the probability wave. But critics argue it does so at an enormous cost, populating reality with an almost unimaginable number of branching worlds, an ontological extravagance that some find philosophically unpalatable. Then we have the mathematical multiverse, a realm of pure abstraction where every consistent equation is a real universe. This model is stunning in its simplicity and completeness, but it exists in a domain arguably beyond the reach of science, as it may be fundamentally untestable by any conceivable experiment. Brane cosmology stands out by offering tangible, if elusive, pathways for verification. The detection of primordial gravitational waves from a brane collision or the unexplained pull of dark flow could one day provide solid evidence. But this model hinges on the existence of extraspatial dimensions that, so far, have completely eluded our most powerful particle colliders. Each architectural plan presents a different trade-off between elegance, explanatory power, and the crucial ability to be proven wrong. This comparative journey is not about finding a single winner, but about mapping the frontiers of our understanding. It forces us to ask what we value more, a theory that is beautifully simple but forever beyond our reach, or one that is complex and messy but might one day whisper its secrets to our telescopes and detectors. The most promising path forward likely lies with the models that leave a door slightly ajar, inviting not just contemplation, but the possibility of a message from the other side. This architectural wonder of the multiverse faces a foundational challenge, one that strikes at the very definition of science itself. The principle of falsifiability requires that a true scientific theory must be capable of being proven false through observation or experiment. If other universes are, by their very nature, forever sealed off from our own, then how can we ever hope to test their existence? The eminent physicist Paul Davies and other critics raise a profound point, suggesting that without a path to potential disproof, the multiverse hypothesis risks drifting from the shores of empirical science into the open ocean of philosophical speculation. It becomes an idea that can explain everything, but in doing so, predicts nothing specific about our own world. This is not a small concern. It challenges whether we are constructing a grand palace of knowledge or merely a beautiful fantasy. Yet, those who champion the multiverse propose a different kind of test. We may never visit another reality, but we can search for its fingerprints all over our own. The specific pattern of ripples in the cosmic microwave background, the ancient light from the Big Bang, could bear the imprint of a collision with another cosmic membrane. The detection of a primordial gravitational wave background with a very specific signature could be the echo of that creation event. Even the mysterious dark flow, that strange current pulling at galaxy clusters, could be the gravitational shadow of a neighboring universe. This shifts the entire endeavor. The goal is not to build a telescope to see another world, but to become cosmic detectives in our own, searching for clues that the local laws of physics were shaped by external, unseeable forces. The scientific status of the multiverse rests entirely on this search for indirect evidence, on finding anomalies within our universe that have no other plausible explanation. This debate is far more than academic. It determines whether this magnificent architecture is a castle in the air or a structure grounded in the bedrock of observational reality. The future of cosmology depends on our ingenuity to probe these ultimate horizons, to listen for the whispers from beyond the veil of our own space-time. That initial burst of expansion was not a one-time event. It was the ignition of a cosmic engine that continues to run, a perpetual motion machine for reality itself. This is the theory of eternal inflation, and it provides the clearest physical picture of how a multiverse could be manufactured. Think of the fabric of space not as a static stage, but as a living, breathing entity filled with a strange, high-energy field. In most regions, this field eventually settles down like a pot of boiling water calming. The energy of that settling field is what triggers a local Big Bang, inflating a tiny patch of space into an entire universe like our own. But here is the crucial twist. The overall background of space continues to boil. It expands so rapidly that new regions of high-energy field are constantly being created, and within those regions, more pockets settle and inflate into new universes. As physicist Andre Linde explains, inflation is not just a theory of our universe's birth. It is a mechanism that produces a multiverse. It becomes a self-replicating process, a cosmic vineyard where new grapes are forever forming on a vine that grows faster than the fruit can ripen. Each of these pocket universes is causally disconnected from the others, forever drifting apart in an ever-inflating metaspace. And because the process is driven by random quantum fluctuations, each new bubble can freeze in a different set of physical constants as it forms. The strength of gravity, the number of dimensions, the very nature of matter, all become a cosmic lottery ticket printed at the moment of creation. This dynamic architecture transforms the cosmos from a single, static entity into a living, frothing landscape, a sea of space-time where new islands of reality are constantly bubbling into existence. This engine does not just create space and time, it populates it with an infinite variety of worlds, setting the stage for every possible physics to play out somewhere. The source of this cosmic diversity may lie in the nature of reality's most fundamental building blocks. String theory proposes that the universe is not made of point-like particles, but of unimaginably small, vibrating loops of energy. The specific resonance of each string, the unique note it plays, determines whether it manifests as an electron, a quark, or a photon. But for this cosmic symphony to be mathematically consistent, it requires more than the three spatial dimensions we experience. It demands a total of 10 or 11. The reason we do not perceive these extra dimensions is that they are curled up or compactified into shapes far too tiny for any instrument to detect. Think of a garden hose. From a distance, it looks like a simple one-dimensional line, but up close, you see it has a second dimension, a circular cross-section curled into a tiny loop. The extra dimensions of string theory are like this, but with far more complex and intricate geometries. Physicists estimate there could be 10 to the power of 500 distinct ways for these dimensions to curl up. This number is so vast it defies all human analogy, a 1 followed by 500 zeros. Each distinct configuration, each unique geometric shape, results in a different vacuum state for its universe. The way the dimensions fold determines the properties of the strings vibrating within them, which in turn fixes the laws of physics themselves. The strength of gravity, the mass of electrons, the very number of fundamental forces, all become consequences of this hidden geometric architecture. This is the string theory landscape, a vast, abstract terrain of possible universes, each with its own unique physical signature. As string theorist Raphael Bauso suggests, the landscape may be the very reason we observe the particular laws of physics that we do. When eternal inflation creates a new bubble universe, it is like rolling a cosmic die with 10 to the 500 sides. The bubble nucleates with a random compactification, locking in a specific point in this landscape and birthing a reality with its own unchangeable rules. Our universe, with its perfect balance for life, is simply one fortunate roll in a cosmic game of chance. This landscape provides a profound mathematical backbone for the Level 2 multiverse, transforming it from a vague concept into a structured exploration of a well-defined set of possibilities. It suggests that while the multiverse is infinite, it is not random. It is a grand, dynamic process systematically unfolding every potential allowed by this deepest layer of mathematical consistency. How does this intricate, hidden geometry influence the way these separate worlds might one day touch? The infinite multiverse presents a paradox at the heart of prediction. If every possible event occurs in some world, how can we ever say one outcome is more probable than another? This is the measure problem, a profound puzzle that challenges our ability to use the multiverse for science. Take the simple act of flipping a coin. In the many worlds picture, the universe splits into one branch where it lands heads and another where it lands tails. Both outcomes are 100% real. So what does it mean to say the probability of heads was 50%? The problem explodes in scale when you consider an infinite cosmos. There are not just two branches, but an infinite number where you are a billionaire and an infinite number where you are not. Infinity divided by infinity is not a meaningful calculation. It is a mathematical dead end. To make sense of this, cosmologists need a way to count the uncountable, a method called a measure. Think of it as a cosmic census that does not just tally worlds, but compares the sizes of different infinite sets. One approach is to consider the rate of branching. Perhaps the universe splits more readily into branches where quantum events follow the expected probabilities, making worlds where coins land heads roughly half the time far more numerous or more robust than the outliers. Another idea is to only count the universes that form within our finite cosmic horizon, our observable patch, where probabilities can still be defined. Yet these are provisional fixes for a deeply rooted issue. This is not just an abstract philosophical game, it strikes at a core promise of the multiverse. If we cannot say that a life-permitting universe is more likely than a barren void, then the elegant anthropic explanation for our existence loses its force. The entire architectural blueprint, for all its grandeur, risks being untestable and ultimately useless for making predictions. Solving the measure problem forces us to refine our intuition about infinity itself, to find a way to weigh possibilities in a reality where everything happens. It is a reminder that mapping the multiverse requires more than just bold ideas. It demands a new mathematics for a cosmos without limits. The crushing grip of a black hole might not be a final destination, but a gateway. According to classical physics, matter falling into a black hole is doomed to be compressed into an infinitely dense point, a singularity where the known laws of physics break down completely. Yet this bleak picture creates a paradox, a conflict with quantum mechanics which insists that information can never be truly destroyed. So where does all that information go? One compelling resolution suggests that the information is not lost at all, but instead passes through the black hole's interior into an entirely new region of spacetime. The mathematics of general relativity allows for this interior to be an Einstein-Rosen bridge, a wormhole linking our universe to another. This theoretical tunnel, first explored in depth by physicist Kip Thorne, offers a breathtaking possibility. A black hole could be a one-way door to a different cosmos, a cosmic birth canal connecting a dying star in our reality to the nascent beginnings of another. For such a passage to remain open and stable, even for a moment, it would require a form of exotic matter with negative energy density, a substance that pushes space apart rather than pulling it together. While we have no evidence such matter can exist in the quantities needed, its theoretical role highlights how the architecture of reality might be perforated with these potential passageways. They represent the most direct and dramatic mechanism for interaction within the multiverse, literal tunnels woven into the fabric of space-time at its most extreme. Though traversing one remains a distant dream, their mathematical possibility reshapes our understanding of cosmic endings. A star's collapse may not be an erasure, but a transformation, a violent event that stitches two separate realities together. This transforms the darkest objects in our sky from ultimate voids into potential connectors, suggesting that the boundaries between worlds are not just abstract, but physical structures waiting to be understood. Our own experience of time, a one-way street from past to future, feels as certain as gravity. This irreversible flow, driven by the constant increase of entropy or disorder, is woven into everything we do. Yet this arrow of time may not be a universal rule, but a local condition of our particular cosmic neighborhood. The ultimate source of our forward-moving time was the incredibly low entropy state of the Big Bang, a condition of exquisite order that set the universe on a specific path toward ever greater chaos. Within the multiverse framework, this starting point was not a unique miracle. Different pocket universes, born from random quantum fluctuations in the eternal inflating background, could have crystallized with wildly different initial entropy levels. In a universe that began with high entropy, time would have no clear direction at all. Such a cosmos would be in a state of perpetual thermal equilibrium, a lukewarm soup where nothing truly new happens and the concepts of past and future are meaningless. Even more startling is the possibility of a universe that began in a state of maximum order on the other end of the scale, leading to an arrow of time that flows in the opposite direction from our own. From our perspective, such a reality would appear to be running backwards, with shattered cups assembling themselves on tables and sunlight flowing up from plants into the sun. As physicist Sean Carroll explains, the multiverse can help explain why our universe started with such a low entropy. We find ourselves in a cosmos with a strong times arrow, not because it is special, but because a clear temporal direction is a prerequisite for the complex processes that lead to life and observers. This architectural feature of the multiverse encompasses more than just different laws of physics. It suggests entire realms operating with alien histories of causality, where effect precedes cause and the very logic of events is inverted. The potential for interaction between such opposing timelines is a challenge to our deepest intuitions. If a signal could cross from a universe with a reversed arrow of time into ours, would we perceive it as a message from the future or as an effect in search of a cause? The fabric of reality may be woven with threads of time pointing in every conceivable direction, and our unidirectional experience may be just a single, local perspective on an infinitely richer tapestry. Every choice you make sends ripples across the multiverse. This is the profound ethical dilemma that emerges from a cosmos of infinite selves. If every possible version of your life is being lived in full by a parallel you, then the significance of your own path seems to shrink. Why agonize over a difficult decision when another version of you has already taken the other path? This line of thinking, known as moral quietism, suggests that in a reality where every outcome is realized, our individual moral struggles lose their urgency. Yet there is a compelling counterargument that expands our sense of duty to an unimaginable scale. If all these lives are equally real, then your actions here might be part of a larger pattern affecting the entire ensemble of you. Perhaps we have a responsibility to act in ways that create positive outcomes for the greatest number of our own lives across the branching tree of reality. This is not about influencing those other selves directly, but about making choices in this branch that align with a broader, more harmonious existence for the whole collection. The philosopher David Lewis argued for a view called modal realism, where every possible world is just as concrete and real as our own. From this perspective, the person you are in this moment is not the only true version, but simply one citizen in a vast federation of selves. This transforms cosmology from a distant science into a deeply personal inquiry. The architecture of reality is no longer just about colliding branes and quantum fields. It becomes a framework that directly challenges how we understand consequence and compassion. It asks us to consider our life not as a single, isolated story, but as one thread in a tapestry of infinite variation, where every choice carries the weight of all the paths not taken. The hunt for our cosmic neighbors is not a matter of building a faster ship, but of building a better detector. Scientists are scouring the oldest light in the universe, the cosmic microwave background, for the faintest of scars. These could be the circular imprints of a universe that existed before our own, or the subtle bruising left by a long-ago collision with a neighboring brane. The most detailed maps of this ancient afterglow come from the Planck satellite, and they hold intriguing, if controversial, anomalies. Certain large-scale patterns appear weaker than our best models predict, and there is a mysterious cold spot in the sky that defies easy explanation. While none of these are proof of another reality, they are the kinds of faint whispers that keep the investigation alive, the cosmic equivalent of a faint noise from the other side of a wall. The next generation of observatories is being designed to listen more closely. The James Webb Space Telescope peers back to the formation of the first galaxies, seeking clues about the initial conditions set by inflation. And future gravitational wave observatories, like the space-based LIGO mission, will attempt to hear the faint hum of the universe's birth. This primordial gravitational wave background would be the ultimate fossil, a direct recording of the violent events that may have created our cosmic bubble. Could its specific frequency reveal the jolt of a collision with another reality? Even here on Earth, tabletop experiments continue to probe the quantum realm, testing the foundations of how reality branches and whether information can truly be lost. This experimental frontier is where the grand architecture of the multiverse meets the hard, unyielding ground of empirical data. It is a testament to the scientific process, a commitment to test even our most fantastical ideas against the cold, clear light of observation. The ultimate judge of these cosmic blueprints will not be their beauty or their philosophical appeal, but the story told by the data itself. What faint signal, hidden in the static of the cosmos, might one day rewrite our understanding of reality itself? A profound challenge to this entire cosmic architecture comes not from a telescope, but from a philosophical principle. Does the multiverse, in its infinite generosity, actually explain anything at all? Critics contend that a theory which allows for every possible outcome effectively predicts none. If our universe's seemingly perfect constants can be dismissed as a random lottery win in a cosmic sea of failures, then have we simply given up on the search for a deeper, more elegant reason for why things are the way they are? This is the charge of unscientific speculation, a retreat from the traditional goal of physics to find a unique and necessary set of laws for our one and only universe. The fear is that by invoking an infinite number of hidden worlds, we can explain any feature of our reality as a mere coincidence, a local fluctuation that requires no further investigation. This debate strikes at the very definition of a good scientific explanation. Is it enough to say that we live in a habitable universe because an infinite number of inhospitable ones also exist, or does that feel like a mathematical sleight of hand? Engaging with this objection is not a sign of weakness in the multiverse hypothesis, but a vital step in its maturation. It forces proponents to move beyond mathematical beauty and seek concrete, testable predictions that could distinguish our cosmos as the product of a multiverse, rather than a standalone entity. The ultimate defense of this grand architecture will not be its conceptual appeal, but its ability to leave tangible fingerprints in our own reality, anomalies that have no other plausible cause. This philosophical pressure ensures that the multiverse remains a scientific proposition, grounded in reason and evidence, and not a metaphysical cop-out that brings the quest for fundamental understanding to a premature and unsatisfying halt. Long before physicists sketched its mathematical blueprints, the human soul was dreaming of other worlds. Every culture's mythology speaks of hidden realms, from the spirit worlds of indigenous traditions to the heavenly planes of ancient epics. These were the first multiverses, born not from equations but from a fundamental human yearning to explore what lies beyond the visible horizon. Today, that same impulse fuels our blockbuster films and novels. In stories like Everything Everywhere All at Once, the multiverse becomes a stage for the most intimate human drama, where a single choice can fracture a life into 1,000 different paths, each with its own joys and sorrows. The Marvel Cinematic Universe transforms this concept into an epic canvas for cosmic conflict, where the fate of every reality hinges on the actions of a few. While these fictional worlds take creative liberties, bending physics for the sake of a compelling story, they serve a profound purpose. They translate abstract, almost unthinkable scientific theories into something we can feel. They allow us to walk in the shoes of another version of ourselves, to ask what our life might have been if we had made one different decision. This exploration of identity, choice, and destiny gives emotional weight to the cold architecture of cosmic inflation and quantum branching. These narratives are more than just entertainment, they are a vital bridge. They take the formidable complexity of the multiverse and wrap it in a human story, making the science accessible and sparking a public wonder that drives our collective curiosity forward. They remind us that the most powerful questions about reality are not just about how the cosmos works, but about who we are within its infinite possibilities. Our minds were forged in a world of solid ground and predictable sunrises, a middle world where cause and effect follow a comfortable rhythm. This evolutionary inheritance leaves us profoundly unequipped to visualize a reality of infinite branching or higher dimensional landscapes. We can write the equations and follow the logic, but truly internalizing these concepts is a different challenge altogether. The physicist Niels Bohr captured this perfectly when he noted that anyone who is not deeply shocked by quantum mechanics has not yet understood it. The full architecture of the multiverse takes that shock and expands it to a cosmic scale, confronting us with ideas that feel inherently alien to our everyday experience. Our intuition, so reliable for navigating our immediate environment, becomes a poor and even misleading guide at these frontiers. we struggle to picture 10 spatial dimensions, not because they are illogical, but because our brains have no reference point for such a geometry. The notion of an actual infinity, where every possible version of your life is being lived, can feel more like a philosophical abstraction than a physical reality. This does not mean the multiverse is incorrect. It signals that we are pushing against the very limits of human comprehension. We are like two-dimensional beings trying to understand the concept of up, forced to rely on the abstract language of mathematics to map a territory we cannot directly see. This necessary humility is a crucial part of the scientific journey. Reality is under no obligation to be intuitively obvious to us. Its rules are written in a dialect far stranger than we could have ever anticipated, and our task is to listen patiently to what the cosmos is trying to say, even when its voice whispers from beyond the horizon of our understanding. The final answers may not come from a single brilliant insight, but from a convergence of three powerful streams of inquiry. The first is a flood of new data. Our maps of the cosmos are becoming exquisitely detailed, charting the distribution of billions of galaxies and the subtle patterns in the cosmic microwave background with unprecedented precision. Within this sea of information, we are searching for specific statistical anomalies, a strange lack of correlation on the largest scales, or a peculiar alignment of hot and cold spots that our standard model of a single, isolated universe simply cannot explain. These faint cosmic fingerprints could be the first solid evidence of an external influence, a brush with a neighboring reality that left its mark on our own. The second stream flows from pure theory, relentlessly pursuing the holy grail of a unified theory of quantum gravity. This single framework, which would seamlessly weave together the vast cosmic scale of general relativity with the probabilistic rules of the quantum world, could either solidify the foundations of the multiverse or reveal them to be a mathematical mirage. Such a theory would tell us if the extra dimensions of string theory are a necessary feature of reality, or if the infinite branching of quantum worlds is an inescapable consequence of its equations. It would determine if the entire architectural plan we have been exploring is built on solid ground or shifting sand. The third, and perhaps most surprising, stream emerges from quantum computing laboratories. While we cannot create a full-scale universe, we might be able to build a sophisticated analog of a multiverse within a controlled quantum system. By carefully arranging qubits to simulate the rules of cosmic inflation or quantum branching, we could watch how these miniature realities evolve, interact, and potentially leave detectable imprints on one another. This would allow us to test the core mechanisms of multiverse models in a tabletop experiment, turning abstract cosmology into an experimental science. The coming decades will see these three paths intertwine, each one informing and constraining the others. Our understanding of reality's architecture is not a finished blueprint, but a living document, constantly being revised as new evidence comes to light and new tools allow us to ask deeper questions of the cosmos. These separate blueprints for reality might not be rival designs at all. Instead, they could be different views of the same magnificent structure, seen through different scientific lenses. The quantum multiverse, with its infinite branching timelines, may not exist apart from the cosmic bubble bath of eternally inflating universes. What if the quantum realm is the very engine that creates them? Every random quantum fluctuation that causes a universe to branch in the many worlds interpretation could, on a vastly larger scale, be the seed for a new bubble universe in the eternal inflation landscape. The microscopic and the cosmic become two descriptions of the same generative process. Our own three-dimensional brain, floating in a higher dimensional bulk, could itself be a canvas upon which the quantum multiverse paints its endless variations. We are not forced to choose one architecture over another. but to see them as interconnected levels of a single, deeper reality. This pursuit of a grand synthesis is the driving force at the edge of theoretical physics. The ultimate goal is a master plan, a unified theory that can weave these threads into a single tapestry, explaining how a reality of such breathtaking variety can emerge from a fundamental set of principles. This is not about finding which blueprint is correct, but about discovering how they all fit together to form a complete picture of existence, from the quantum grain to the cosmic horizon. Our journey across the cosmic map of reality is complete. We have wandered from the endless shores of identical bubble universes to the quantum crossroads where every choice carves a new world, and finally into the abstract realm where mathematics itself breathes life into existence. We have felt the faint gravitational pull of a neighboring brane and pondered the threads of entanglement that might stitch the entire multiverse into a single, coherent whole. This grand architecture reveals a cosmos of unimaginable richness, where our familiar universe is not a solitary island, but one vibrant thread in an infinite tapestry. The takeaway is both humbling and exhilarating. Our reality is likely part of a much vaster, more complex, and more wonderful whole than we ever dared to dream. While a final, definitive proof still waits beyond our current horizon, the multiverse stands as the boldest and most logical extension of the equations we already trust to describe our world. Let this exploration be a beginning for your own curiosity. What does the possibility of infinite realities mean for your own story, for the weight of your choices, or for your sense of wonder? Share your most mind-bending questions and personal reflections in the comments below. We would love to continue the conversation with you. If this voyage through the nature of existence expanded your perspective, consider subscribing for more deep dives into the mysteries that shape our universe. Remember, the final frontier is not just the space between stars, but the very architecture of reality itself.